Okay, so good morning, everyone. Here we're going to be continuing our conversation from last class. We will now be diving into the law of large numbers and central tendency. But before we do that, let's take a moment and let's remember what we talked about last time. What did we talk about last time? Eye charts and bar charts. What do you mean? What do you mean? Okay. Good, Michael. Yeah, I agree with that.
And somehow it's hard to see number stuff on the eye chart.
Yeah, sometimes it's hard, especially when there's a lot of individual categories, and so those wedges get really small. I'm absolutely right, Cassandra. Absolutely. Anything else we talked about? We also did scatter plots, if you recall. What's the deal with scatter plots? Anything you remember?
Linear and log scale.
I can't remember your name though. Gabe. What do you mean linear and log scale, Gabe?
Like on the X and Y axis for scatter plots, whether you should use those linear or log scale, like what's more appropriate given the
How do you determine what's more appropriate?
So like the log increases by a lot more than the linear, so the log kind of multiplies, and the linear is more for it's like close together.
Yeah. So log is best for if the data is really spread out, like we saw with GDP, with average income, with GDP per capita. How it can be really, really small in the hundreds, or it can be really, really big in the hundreds of thousands. And linear is better when the data are already pretty close together. So you don't need to make that situation worse. Or if you establish a log scale when they're already pretty close together, they're really going to scrunch everything up. You really can't tell anything. So both are good in different situations. And it's really like the best thing you should do, honestly, because it's so easy to switch from log to linear in Excel, to just try it out and look which one looks better, which one's where you can see the individual data points easiest and where they might land easiest. Okay. So today we're diving into the law of large numbers. And to begin our conversation on the law of large numbers, let's consider a single coin. So this is a quarter. It is a fair coin. Take my word for it. If I flip it, what are the chances it comes up head? What are the chances it comes up tails? 50-50. You want to say 51. You think I'm just a cheat. I said it's a fair coin. Oh, there's more on the heads. I thought they balanced, but just shut up. So, wait. So if you're saying there's more weight on the heads, so doesn't that mean that the tails then comes up more common because it weighs it down?
I remember watching the video and they explained everything. I was taking 149.
Okay, we're gonna go 50-50 today. Then they were saying it's 51s the no tails.
1%
But if the heads have more weight, then wouldn't the heads bring it down? So it's on tails. Yeah. Okay. So we're just gonna set that aside for now, and we're gonna flip the coin. I flipped the coin. What did I get? Tails. Okay. So I'm testing to see. So we're gonna test, right? And we're gonna test to see if this works. And I just flipped it, and I got tails one time. So while you're saying, oh, it's 50-50 or 51-49, I tested it, and I got 100% of the time I flipped it, I got tails. So...
But you flipped it once, so of course it would be 100%.
Well, it could have been heads.
But you still flipped it once.
Well, yeah, so we can only, okay, fair. Yeah, possibly come out like 50%. Okay, so now it came out heads.
So that's different.
So we're good, right? Yeah. So I'm done. There's no way it could have come up tails twice. Usually, by the way, when I do this a fair number of times, it comes up twice in a row. So 4.1 half happens. It didn't happen this time. So does that mean I only had to flip it twice? Like, if you were to come to me like, David, test to see if this coin is fair, you only have to flip it 2 times. Would that be reasonable?
No.
Why not?
Because I'm everything else tails twice.
It could have. That's true. It could have come up heads twice as well, right? What is the chance of it coming up tails, tails?
0.
25%.
It's a 25% chance. Why is it 25%?
Because it's 50% on the first try. You know, on the second try, it's also
Mm-hmm.
it's only 50%, but then if you divide 50 by 2, it's 5%.
Yeah, you multiply the two together. You multiply one. Well, we'll talk about this when we do probability.
Okay.
But yeah, we multiply the two together. You get 1/4. But you know, what are the so? In order to understand why it's 1/4, take a moment to recognize what are the different possibilities. You can get tails the first time and tails the second time. You can do what I did and get tails the first time and heads the second time. What are the other possible outcomes? And heads, tails. There are literally only 4 possible outcomes. Each one is equally likely. Thus, each one has a 1/4, 1 out of 4 chance or 25% chance of happening. Now, which of these results ends up with an empirical result, something you can point to? Having a 50% chance of heads and a 50% chance of tails. Which of these results?
Heads, tails, tails, heads.
So we have 2 options, right? We can get tails and then heads, or we could have gotten heads and then tails.
Yeah.
In other words, we have a 50% chance of getting the theoretical result. But we have also a 50% chance of not getting the theoretical result. We have a 25% chance of getting something that is way too high. And we have a 25% chance of getting something that is way too low in those results. So arguably, this is kind of, if you come to me and you're like, you should flip it just 2 times, and then you'll get an even number, and it'll be half of one, half the other. You're really playing with fire, right? There's a 50% chance also that I'll just get 2 things in a row. It might be 2 heads, it might be 2 tails, but it'll be way off compared to what the theoretical probability is. So let's imagine that, so maybe we should flip it 4 times, right? 4 is better. Why is 4 better than 2?
More data.
What?
It's more data, so it's more
More data, more information, right? So here's the chances. So I could get heads. Heads, 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 heads. This is all the different combinations I could get. And note, of these 1, 2, 3, 4, 5, 6, 7, 8, 16 different possible results. 1, 2, 3, 4, 5, 6. 6 of them are exactly what I would like to see. Exactly what I would expect to see, I should say. What is 6 divided by 16? 37.5%. Use that method, right? You didn't just like look right here where it says 37.5%.
I mean, I actually do.
Oh, wow, okay. We're gonna, that's awesome. So he's absolutely right, 37.5%. There's a 37.5% chance you would get the right answer, the theoretical answer. That's lower. Before, we had a 50% chance of getting the theoretical result. Now we have only a 37% chance. Seems like this is worse, right? How is this not worse? Anyone? Question is, before, when I only flipped it 2 times, I had a 50% chance of getting the theoretical results. When I flip it 4 times, I only have a 37% chance of getting a theoretical result. But everyone said that if I flipped things more times, flipped it more times, that would be a better sample size than if I flipped it only a few times. So why did the likelihood of me getting the quote-unquote right answer, the theoretical result, why did that fall when I flipped it more times?
You have more probabilities.
What do you mean?
You get X more often or X more often.
Yeah. Wait, I'm not sure what you mean.
I don't know.
Okay.
The average amount of times that comes up
In the average number. Well, but it's we have a lot of heads over here, but we have a lot of tails over here. It's actually made it so it's very symmetric.
Well, you only have like a 50% chance of it actually being theoretical.
Yeah, now I'm with a 37% chance. 37.5.
But that was like a 50% chance of that happening.
There's what?
There's a 50% chance of that happening.
Of what happening?
Of it being 37.5.
No. There was so before there was a 50% chance of me getting the theoretical result of half a page.
Yeah, but if you look at
Now there's a lower chance of me getting the right answer of getting a 50% chance.
Yeah, but if you look at like the other ways of getting, you could get tails, or heads, or 25% chance of getting it tails, heads, tails.
Yeah.
That would it skews the data, so it's not theoretical.
Yeah. So you're absolutely right. So don't think about, the likelihood of me getting the precise answer has fallen. But the likelihood of me getting way off has also fallen, like by a lot. It used to be a half a chance of being way off, of being way too high, 100% chance, or way too low, 0%. Now these are the only times it shows up. It ends up being at 12.5%. So it goes from 50% being way off to 12.5% of being way off. And the rest are things that are kind of close. Is 25%, 50%, obviously not spot on, but still pretty good. So this is an improvement, right? While I'm less likely to get the perfect result, I'm also a lot less likely to get the really wrong result. So on average, I actually do pretty well. We're going to flip it 10 times. Here's a distribution of those results. Note the most likely result, and normally that was the case here too. The most likely result before 37.5% was also the theoretical result, and that's the case as well. The most likely result is the 50% chance, and ones that are also pretty likely at just over 20% chance each are 40 and 60%. That's pretty close. And the crazy ones, 10 tails in a row, 10 heads in a row, is a shockingly small result. That frequency distribution. So in other words, a larger sample size is more important. Well, it's possible that maybe when I did it right now, I get this result like I did before, and then after I flip it 8 more times, I get nothing but heads, and so I think the result is this, right, which is way off. It's possible that I could actually do worse, but the tendency is for larger sample sizes to be more accurate. And this is what we call the law of large numbers. As sample size increases, the empirical average. What we're measuring with data. Approaches the theoretical average. Any questions? It just makes sense, right? If you have a really large data set, for example, the likelihood of you getting an oddness multiple times in a row is pretty low. If you have a really small data set, the likelihood of you getting an unusual result multiple times in a row is pretty small. It's no different than we were talking about how precise samples are. So, with that in mind, let's talk a little bit about some application. What is this? Roulette wheel. Exactly. How many of you have seen a roulette wheel at the casino? Great. So, how many of you have played? Few of you. You will see when you go to the roulette wheel, not only the wheel and the little thing and the person who spins it and people putting money on this little board here, you will also see a display. What does the display show you? Last results. They go back, like, I can't remember how far they go back. 15? Okay. So, let's imagine, Rolando, you go to the roulette wheel, and you see the past few results have been 20, 26, 4, 15, 35, and 2. The past 6 results have been these. What goes to your mind? What would all these have in common? They're black. That's all right. These are all black. So, what do you do? Just play around. Just play along. What do you think? What do you think most people do when they see that? It's going to go red, right? But I think most people go red. Yeah. We'll talk about what you're talking about later. Yeah. But like that one really loves black, right? That comes up, and we'll talk about that problem later. But most people look at this and they're like, oh, red has got to come up. Red is due. Right? And I've actually, I once went to a conference in Vegas, and I actually had an economist tell me this. And he cited the law of large numbers. And you can kind of see where he's coming from. Like, look, on average, a little less than 50% of the time, it should get red. A little less than 50% of the time, it should get black. I say a little less because we have the green ones, which throw that off. That's how the casino makes the money, the green ones. We'll talk about that when we do probability and expected value. But, so, it should be about half either way, a little less than half either way. And here, we have 6 in a row that's saying it's got to be red. I'm sorry, the 6 in a row has been black, so it's got to be red coming up, because if it's not red coming up, then the law of large numbers doesn't happen. You know, it's got to even out. Red is due. Now, how many of you agree with that? Careful. It looks like most of you don't agree with that. And you are right not to agree with it. Because believing that red is due is what is a misapplication of the law of large numbers, and it's what we call the gambler's fallacy. Why Why does it not make sense that red should come up more often? Yes, CJ. Slightly less than 50% chance. Yeah. So, but then why shouldn't it approach? Why shouldn't it approach red then? Because I mean, it's got to be 50% chance, a little less than 50% chance on average, right? What?
Yeah, they don't.
Who said?
And they don't impact the next result.
I'm not sure what your name is. Trying to remember.
What? Anisha. Way off. Okay. So Anisha is absolutely right. She's absolutely right. It doesn't know. It doesn't remember that it did black like 6 times in a row. It's a hunk of wood in a circle with a bunch of colors on it, and it's spin. It's a matter of physics. It doesn't know. It's random. Each spin of the roulette wheel is what we call, anyone know because with an I? Independent. Each spin of the roulette wheel is independent. In other words, the result of previous trials does not influence future results. Yeah, Anisha. Yeah, 21. So in that case, they're able to expose the fact that when you draw cards from a deck, as you do in 21, then the likelihood of any card coming up is not independent. Because if you draw up an ace, then that means the next card is less likely to draw up an ace because one of the aces have been used. And so this statistical technique card counting addresses the fact that each pull of the card is not independent, and then you can sort of tease out some probabilities and see how the probabilities change. And it's really hard to do, which is why I took people from I think you're right. I think it was MIT. Took people from MIT, studying a lot and practicing a lot to try to break Vegas. And now they try to combat that too by in any deck of cards, it's actually multiple decks of cards. So it's harder to predict. And you don't know how many decks of cards they're using. So it's harder to figure out. They saw that and they tried to fix it. But that is not the case here. So a gambler's fallacy looks at results that are underrepresented, like red hasn't come up in a while, and believes that they are more likely in future independent trials. So does that mean that the law of large numbers isn't true? Because I'm just saying to you, no, I don't care that we've had 6 black in a row. The chance of it becoming red or black hasn't changed. And it's just as likely that there'll be another black and there will be another red. How do you reconcile the gambler's fallacy with the law of large numbers? Ike.
It's giving you an odds in the law of large numbers, but it's not predicting results.
Tell me more. What do you mean?
Like, it can just tell you that there is a 50% chance that red could come up. But it's not predicting that red will come up at a 50% sample rate.
Yeah. In other words, like we're saying, look, over the long run, it could, right? That word approaches is very important. It's like tends to, but with no guarantee, right? I could, like I said, I could flip a head and then a tails, and I could flip, and that seems like that's spot on. And then I could flip like 8 more heads in a row. right? And it actually deviates away. But you can't predict in any individual check because you're trying to predict a whole string of possibilities. Imagine that there is a large population of possibilities that have been already predetermined randomly, and it goes on for an infinite number of times. And if you look at this whole string, this population that goes on for an infinite number of times, it's going to even out, right? As the theory would suggest. Half one, half the other, or, some of it red, some of it green, and then the little rest of it. I'm sorry, some of it red, some of it black, the little rest of it green. And when you spin the roulette wheel, you are essentially dipping into that string and then starting. And it could be in that string, you could have a whole bunch of black in a row, or a whole bunch of red in a row. But believing that you know what's coming up next is thinking that you understand the whole infinite string when really just looking at a part. So an example of this is that I've heard a story of this stats professor who gave his students an assignment to take a coin and flip the coin, maybe it was 25 times? Maybe it was 50 times? We'll say 50 times. Flip the coin 50 times and record the result. Now, you ever tried flipping a coin 50 times? It takes a while. You flip it, sometimes you'll drop it, you have to find it again. So, some students naturally think, I'm not going to flip this thing 50 times. He doesn't know. I'm just going to write tails, heads, heads, tails, heads, 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 tails, heads. Do it in like 2 minutes, done. But he can always tell who flipped the coin and who just made up numbers or made up results. How do you think he can tell between the people who flipped and the people who didn't?
So big a probability that's like really, really unlikely.
What do you mean?
Like little
Heads and tails.
But like you said, so like it'll like the larger, like the low number of states, like it'll go towards the theoretical average. Mm-hmm. So like they may have picked a probability, or they may have picked like one of the scenarios that was like way on the outside. That was like a 10% chance, likely, when he would be expecting like everything to be relatively in like the 40 to 60% range.
Wait, so you're saying that the people who are making up the numbers are going to write a whole bunch of heads and no tails?
No, I'm not saying that, but possibly. Actually, yeah, possibly. Like, I don't know, I guess.
Because, if you haven't had any stats before, and I told you to flip a coin 50 times, you would think that you would need 25 heads and 25 tails, right? Maybe you go 26, 24. Maybe if you're feeling daring, 27, 23. But you'll do about even numbers. And you'll also do it with regularity. Right? A few tails, a few heads, maybe a tail and a head, a few tails, a few heads, a few tails and a head. It turns out that, at least according to legend, if you do this, inevitably you will get a string of like 8 tails right in a row. Or 8 heads right in a row. It is sometimes, but if you flip a coin enough times, you're going to get that string right in a row. So that's how he figured out if people actually did the assignment or not. People who made up the numbers had this regular kind of consistency. People who actually flipped it would inevitably get a string of one or the other. Just because you're pulling from this big thing, and sometimes one comes up more than the other. Sometimes it just happens a lot in a row. It doesn't disprove the law of large numbers, it just says that you can't, while it is a law, the law is kind of soft. The law is kind of soft. To illustrate this, some people really believed in the gambler's fallacy back in August 18, 1913. Now, 6 black in a row is pretty unusual. In Monte Carlo, in 1913, how many black do you think they got in a row? 20? 20 black in a row? That's ridiculous. It was 26. It was, 26 times in a row, black came up. So imagine, you saw the black there at 6, and you're like, oh, well, red's definitely coming up. And then it came black again at 6. And people lost money. And then at 7. it was black again. And then 10, it was black again. And then 15, it was black again. And then 20, it was black again. 26, it was black again. And they're like, oh my God. Like, people lost a fortune betting on red. They lost a fortune betting on red. It can happen, right? It's unusual. That's why I have it in the notes, because someone like, that was weird, right? But people lost millions because they believed in the gambler's house. Don't do that, please. It doesn't know. It doesn't know. Did you have your hand up? Okay. Yes.
So if you were to go to a casino and play that game, how would you apply the large numbers to win, like, certain rounds?
Oh, you can't, because it's random. You don't know. There was a show called Breaking Vegas where they did get, in the early days of like computers, they did get some people to try to break roulette, because roulette is ultimately about physics. You know, you roll, you spin the wheel, and then you put the ball down, and it's going to be, at that point, it's theoretically possible to calculate that if you let it go at 18, maybe it's more likely to hit these numbers than these numbers, because you know just where it falls. And I remember some story of people like figuring it out, but it required a lot of calculations. So they built a computer hidden into their pant leg, and then I think it was like you put your hand in your pocket, and that's how you input where they let go of the ball, and then the computer would output where they think it would land, or at least the numbers it wouldn't land. And it would be like by poking your foot. It would do it like Morse code or something. I can't remember how they did this exactly. And then that was enough to say, oh, they can eliminate with a reasonable amount of chance certain numbers on this roulette wheel. And that is enough to tip the scales to now make it on average that you win money, because the profits are pretty narrow. So that's one way to do it. I think they walked for that out. So it was a lot harder to do it anyway. Any questions on it? Let's go back to what Rolando said. You want to say, oh, no, maybe it's more likely that it's black because it's gotten good at black. And that obviously is silly too, right? That's not what you said, that's what you said other people will say. And that is obviously silly too, but it's a different example of this sort of problem. We call this the hot hand policy. What is the rookie of the year in baseball? Anyone know what that is? Mm-hmm. Yeah, exactly. He's the best new player that year. He's the best one. And baseball is interesting from a statistics standpoint because baseball is an unusual sport. It doesn't involve like getting in with a lot of other players. It's a kind of a solo sport in a lot of ways. I mean, obviously there's some team element to it, but when you're at bat, you're the only one at bat. And when someone's pitching at you, they're the only one pitching. So you can sort of gather a lot of data on any one particular person and be able to claim with a reasonable amount of accuracy that this data relates to this individual, batting numbers and all that stuff. So as a result, there's a lot of data on rookies, on all players. And they can say, wow, this rookie was particularly good. They had a really high batting average. They struck out a lot of people. They caught a lot of balls, whatever it was. And they're the best ones. And the rookie of the year tends to get a lot of press. Does anyone know how the rookie of the year fares? Are these the beginnings of new baseball stars?
Sometimes.
Sometimes? Usually?
It's not like on-base percentage is the most important statistic.
What?
Like on-base percentage is like the most important statistic.
Okay, so if someone has an on-base percentage, that means that they're going to be really great?
Well, usually if they have a higher on-base percentage, that means they have more of an opportunity to score.
Okay. But you didn't answer my question. I'm asking, historically, do people who have that high on-base percentage, do they tend to be great players? Legendary ones that we hear about.
They tend to be overlooked sometimes.
Yeah. they tend to be people that actually don't do that well their second year. In fact, the rookie of the year tends to not do very well the second year at all. They tend to actually do pretty bad. And one theory is, oh, it's because they got arrogant, because they got rookie of the year and they lost their way and they just don't do well. But the other reason, another reason is they just got lucky. And you are mistaking luck for skill. You are accomplishing what we call the hot hand fallacy. We're over-representing groups, or representing results. Are more likely. In future independence trials.
I have a question.
Yeah.
Since there's more data on the rookie now, then next year wouldn't teams be more likely to change their style against the rookie so making sure that the rookie will play as well the following year? So let's say the rookie is not as good as against left-handed.
Yeah, maybe they're adapting their strategies too, right? So it's a lot easier to fall into the hot hand fallacy because hot hand fallacies typically come up in games of skill. And so maybe the person really is good and they got arrogant. Or maybe the person is good and they're working against them actively, the opponents are working against them. Or maybe there is such a thing as being in the zone and you're free of distractions. But it's also possible that people just get lucky. If you take 201 with me, you realize that it's really hard to beat the stock market. It's very hard to do better on average than the stock market. The stock market is a really hard thing to beat, to predict. It's essentially, day-to-day fluctuations are essentially random. So if you think about all the people who are trying to make money at the stock market, all those active people, all those people who are actively trading, on any given day, half are going to be winners and half are going to be losers. And if you go many days in a row, half of those winners are going to lose and half of those winners are going to win again and again and again and again. And so when there's, a million people at the stock market after, 10 or 20 days, there's still going to be a few people left that won many times in a row. It doesn't mean they're geniuses. They could have just been lucky. The hot hand fallacy actually comes from basketball. There's some stats on basketball, especially for free throws. And when they do the analysis, when we do analysis of that, okay, is a person who's made a lot of baskets, are they more likely to make future baskets? Again, it's hard to tell because it's an interactive sport, but on free throws, you get rid of a lot of that, and they're not more likely. They're not more likely. So, again, it's harder to detect because it typically doesn't come up it typically comes up in games of skill, so it's harder to isolate. But the underlying idea is just because you see someone who's really good doesn't mean they are actually really good. Just because they have a lot of successes doesn't mean they're a master. They could have just gotten lucky. And you might be very well fooled by randomness. Any questions on that? All right. Let's switch gears slightly. As we take a look at the law of large numbers definition, if there's no questions on this. No? Great. You see that we have actually a nice wording in here, empirical average. Averages come up a lot in statistics. In fact, we use average a lot, sample averages a lot. And it's because it's one way we can get what's called central tendency. Whenever you get a sample data, you want to know stuff about it. Things like its dispersion, something we'll talk about later. Also, we typically want to talk about its center point. A single number which captures the center of the data. That's the central tendency. Captures center point of the sample. There are 3 different measures of central tendency. They all begin with M. You're probably familiar with them. Mean, median, and mode. So, what's the distinction between these 3? I don't want to give me any definition. Yeah, Gabe. Mean is the average. Mathematically, what is it equal to?
The sum divided by the total.
So we got our summation notation. Everyone knows what this symbol means, right? Sum. And how do we do the sum of x, I? So what would be in the denominator? What would be up below the summation notation? Well, I mean, we're going to divide by something, but just notation-wise, we have I equals 1. And at the top, you know, so what goes there? Anyone? Either exactly what I'm looking for or conceptually what goes there. The largest value. Largest value. So what we're doing is we're saying I is a subscript. We're going to say I equals 1. So we'll start with the first observation. Well, x's are the values in the values of observations. Example. And we want to go to the last observation, the total number. Does everyone know in statistics what we call the sample size, how big the sample is? A lowercase n. So you go up to the nth observation, the nth observation. So xn would be the last one you have listed. And then you divide, what do you divide by after you add up all of these, the values of all these individual observations? What do you divide by? How many you have, which is n, our sample size. We have 2 other ones. Or 2 other ones. Name again is Aziz. The middle value, yeah, something we talked about before. We had another name for it. Give you a hint. The same thing as the second quartile. In other words, half the observations are below this number, half the observations are above this number. By the way, how do you possibly pick a middle number if you have an even number of observations? Average which ones? Exactly. So, in the case of 1, 3, 5, and 12, the median is 4. The average being of 3 and 5. What is mode? I can't remember your name though, I was trying to remember it. Jeanette. Excellent. Remember that occurs most often. Most common number. The mode is sometimes given a bad rap. It's sometimes like laughed at because it does have some significant disadvantages. But there is a time when mode is really often used. When do you most often use mode?
Frequency,
Okay, what do you mean?
when you want to know the frequency of a certain outcome.
Can you give me an example?
Test scores, you can use mode to find out like how many times, how likely is it that people get A's.
Interesting. So in other words, when you're talking not just the individual's test score, like 82 or 98 or 78, you're talking about the range that the test score goes into. You're talking about categories. And you're absolutely right. Best for categories. You use mode every time you look at a pie chart and you look to see what the biggest wedge is. Or a bar chart, which is the largest number. Oh, that's the mode. That's the most common one. So it's best for categorical data. But mode has some significant problems. I'm going to write a little bigger. There we go. I want to switch colors too. I'm getting tired of this black. So, what are some of the problems of using mode?
It can be misleading.
What do you mean?
Let's say you have like a bunch of numbers that are scattered like between like 100 and 200, but they're all different numbers. And then you just have like two numbers that are the same, which is just like with a value of 1.
Yeah.
And so the mode would just be 1, but so it would be misleading.
Yeah. You can mask important trends or changes or attributes about the data. And not much of a difference between trend and changes, but yeah, basic idea is absolutely right. Case in point too, what do you think the modal hourly wage is? What is the most common hourly wage? Minimum wage. I'm sure that's the case. You know how I'm sure that's the case? What makes you think I'm confident that is the case?
People will least one possible.
Well, that's true. And so they're gonna hit the floor, but of course, not everyone makes the minimum wage, right? Minimum wage is actually not very common. Only a small percent of people make the minimum wage. Why does it not make sense then to say, oh, we should cite the minimum wage as more like what's deceptive about that?
It's the only set with income in the country. Like everybody makes different incomes, but the minimum wage is set.
Yeah, people's individual income is all over the place. If you think of like, a lot of people, for example, get a salary, and the salary might be something like, $32,869. But if we wanted to convert that into an hourly wage, you divide by about 2,000, because that's roughly how many hours a week people work. 40 hours a week for 50 weeks out of the year is 2,000. Obviously, they might work a few more hours, so you might be divided by 2001 or 2008. Well, they may be working a little fewer hours. You might be divided by 1950 or something like that. But you're going to get some we'll even add some cents here. You're going to get some weird number that's going to be, maybe that's $16.56. I don't really know how much it is. But probably something close to 43 cents, 44 cents. Well, I saw that 9, so I wanted to round, but you're right, it would be rounding down. All right. And then technically it goes on to more decibels. So how many people make exactly $16.43? Not many. So with a continuous variable like this, with a quantitative data variable like this, the actual values are all over the map. And the likelihood that you're going to get a significant number of people who all have exactly that value, because maybe some people will have 1644 because maybe they got like a $2 raise and that throws it off. Right? That changes everything. And that means they're counting as something separate. As separate as if that person made $160 an hour. So it has trouble with continuous variables. Also, one other problem with mode we might have more than one. Remember, what is central tendency defined as?
Single number.
A single number. It's 1. But you could have like 4 modes in a data set. You know? You could have no modes, technically, or all modes. It depends on how you look at it. If I view your data set, it looks like this: 1, 2, 2, 3, 3, 4, 4. You have 3 different modes. Right? That's not really informative. It's like, well, it could be 2, it could be 3, it could be 4. It's like, well, yeah, that's like most of it. Good job. It's not really descriptive. So there are lots of little issues with modes that come up. It's really fantastic for categorical data. But we typically don't do too much with modes. Typically, when you see data reported, good data, it will report the mean and the median. So let's unpack a little bit about what's the advantages and disadvantages of those. Does anyone have any questions, by the way, on mode? So, I pulled up some data on the class of 2016. Student debt. So, and this isn't necessarily based on undergraduates, this is based on everyone. People who graduated in 2016, how much debt do they have? That kind of thing. Now, what do you think the average student debt is? Hmm? 1,000? 20,000? Higher than that. 100,000? But I'm looking for the average. So I'm looking for the country. By the way, this represents 44 million borrowers. So there's a lot of borrowers out there. In fact, I don't think this is class. I don't think this is like it labels it a class of 2016, but I don't think that's people who graduated. I just think that's the data that we have. I'm pulling this from the Pew Research Center. Okay. I guess I can just do some numbers. So we can do that. We can figure it out, actually. haven't ran these numbers yet, so this is kind of this will be fun. What could possibly go wrong? Oh yeah, so this should be right. Okay. So, one Pew Research Center, Americans owe more than we'll just round it to $1.3 trillion in student loans. And we have 44 million borrowers. That's how I knew it can't be class of 2000. I think this is slightly different data. I'm mixing up my data now. But this is 2016 numbers, so let's do 2016. What is 1.3 trillion divided by 44 million? Does anyone want to do that math for me? By the way, make sure you get your decimals right. So I'm just going to put this in billions. There we go. Put that in billions. So this is 0.044 billion, and this is 1,300 billion. I'll do that math. No one else is going to do that math. I'll do it. Okay, yeah, that looks about right. I get an average of 29,545. No, dollars per person. So this is, because this was all in billions, so the billions were canceled. This is average student debt. This is average student debt outstanding. This isn't limited to new graduates. That's 2016. It's about $30,000. So, does that seem like a lot?
Not really.
Not really, interestingly, not really. Because keep in mind, it's an average. So this is including people who have a little bit of student debt, but have mostly paid it off. This is not new graduates. New graduates, I think, is something like 37,000 or something like that. You don't think it's that high? Okay, wow, that was not expected. People are like, wow, higher. But what do you suppose the median is? So I give you the average, the mean. What do you suppose the median is? Do you think it's higher or lower? Let me ask you that. Higher. The median is higher. Why do you think the median's higher?
Because there's a wide range.
What do you mean? Sorry, what do you mean?
I don't know, pretty much factor it over to 200,000.
That's true.
So it's like a really wide range. So therefore, $29,000 is close to $5,000 and $200,000. I don't know if that makes sense.
So when we put in the median, because keep in mind with the median, very high values are treated the same as sort of high values. So if we're trying to find the middle number, someone with 30,000 would be above average, but someone with 300,000 would also be above average. They'd be treated the same. So it turns out the median is actually a bit lower than the mean. Do you want to take a guess as to how low it is?
17,000.
15.
How did you do that?
I was like, that's completely random.
So according to the Pew Research Center, all adults. Oh, I'm sorry. It wasn't. Weird. Okay. No, that's right. That's not the wrong thing. Yeah. 17,000. Impressive. Good guess. So it's actually significantly lower. The median student debt is significantly lower. Why? Why is it so much lower?
I feel like there's a lot of like universities that charge like a lot of money. So they go to 4 years, like something back there said, they go to 4 years at like a $30,000 school, they'd have $120,000 worth of debt. So there's a lot of those schools around every state has one. So and
That's
they
true.
also hold a lot of students. So that would bring up the median, I would think. So therefore the median would have to be lower.
That's true, but if it represents a lot of people, then we would expect the median to actually be, be a bit higher, right? Because now you're having more observations really high. We have to be careful about the what you see as what they mark as tuition when they say $30,000 a year for a lot of these schools. Very few people are charged $30,000 a year. You are looking at the sticker price. You're not looking at the net price. The net price is the $30,000 a year, and then scholarships. So it's always a bit lower. And what they call scholarships is another word for discounts. So the maximum amount that schools are charging has been increasing a lot, but they charge a higher amount because they want to charge really rich people a lot of money. So if Mark Zuckerberg sent his kids to college, they're paying $30,000. Most people aren't. So we can't, that's the case. But that's a relatively small part of the population that's being charged that amount. There are some people though where they don't freaking care. There's not a big difference between the net and the sticker price. There are some schools where there's very little difference between the net and the sticker price, and they will charge you even more than $30,000 a year. You know what those schools are called? No. Sometimes, but not always. Medical schools and law schools. You talk about debt, you talk about law school debt. And you talk about debt, you talk about medical. Oh my God, medical students have so much debt. Are we really upset that medical students have a lot of debt?
No.
That people who become doctors have a lot of debt? No, why? You just don't like doctors.
Just like surgeries cost a lot of money.
They make a lot of money. Yeah, that's actually why they make. One of the reasons why they make a lot of money is that they insist on it because they have to pay back all their debt. And schools know that these individuals are in a good position to make a lot of money. That's one of the reasons why those tuitions are so high. But when we put in those debts, those lawyers and those doctor debts, they're included in this total trillion amount of debt, this whatever 1.3 trillion amount. And that those outliers, those unusually high numbers throw out the accurate result. And they throw it off. So the median is actually much lower. It's actually closer to 17,000.
Can you go over the specific notes on the problems of using
I will right now, actually. So this was just an example of this larger conversation when you choose between the two. You'll remember why I was sticking with it. One, median. I'm actually just, I don't know how to do this. Need more space. Oh, I know, it was right here. Median isn't particularly influenced by outliers. Does anyone know what an outlier is? Yeah. Gabe?
It's like, it's either like really small or
Exactly. It's a really unusually large or unusually high or unusually low value. Right. Like those doctors and lawyers who have a bunch of debt, they throw off the average. But in a median, they treat pretty high numbers as exactly the same as very high numbers. Hey, we're looking for the middle number, half the observations on one side, half the observations on the other. So, because of this, the median is best for determining a typicalness, determining a typical observation. You want to try to, like, maybe before you go to, even before you start at school, you want to try to guesstimate how much debt you'll end with. Check the median number. Check the middle number. That's the typical one. Half or higher, half or lower. You want to try to guess your median income? Half or higher, half or lower. You can see huge differences. I have some data too on mean household income in 2012. Was 71,274. Median household income, though, was $20,000 lower than that, at 5117. So significantly lower, because again, those very high incomes are throwing off the data, throwing off the numbers. Yeah.
What is the last word?
So last word, observation. Observation. So it sounds like that mean is stupid. Mean gets irritated and distracted by these really big numbers. Like walking around like with a small child who sees something pretty and wants to run after it. Like, what are you doing, mean? So should we ever use mean? What's the advantage of using mean? What do you suppose the median number of cigarettes people smoke a week is in the United States? Well, let me ask you this. Do you think half of American adults don't smoke? Do you think most American adults don't smoke? Yes. Yes, most American adults do not smoke. So what is the median number of cigarettes smoked? 0. It would be 0 if 51% didn't smoke. It would be 0 if 100% didn't smoke. So in some ways, the median can be deceptive. The median can be deceptive. It can also mask important changes. What's nice about the mean is it literally takes the value of every single number and considers not just where it is on a spectrum, but how big it is. If we looked at the mean cigarette smokes, we would see a difference. If 51% didn't smoke or if 100% didn't smoke. 100% didn't smoke, the mean would be 0. If 51% didn't smoke, it would be more than 0. It would be maybe much more than 0 if we're trying to figure out, say, there are a few people that are heavy smokers or something like that. I'd say that the median isn't particularly influenced by outliers. That is both good and bad. It's good if you don't really care about the outliers. You're not going to law school, at least not right now. You might later. You might become doctors later, but not right now. You don't care right now. So you sort of want to treat those observations as maybe just very high. You don't care about how big they are. But the mean is best for figuring out the big picture. Or thinking about the big picture. If you want to, say, work in finance, and you're like, oh, should we do more student loans? Should we allocate more resources to trying to sell to students for student loans? Then you do care about those outliers a lot, because they matter just as much as someone who doesn't borrow very much money. If you run a store, you don't really care too much about maybe what a typical person buys at the store, how much they typically spend. You do want to care about a lot about the average. That's much more important. They're both useful in different ways. But typically in this class, we talk a lot about the big picture. We're trying to understand the whole sample. So when we work with the data, when we do calculations like standard deviation and other things, we will rely on the mean. With that in mind, I'll let you go and I'll see you on Tuesday. Have a great couple of days, everyone. I'm sorry, I'll see you on Thursday.